So we actually have a special notation when we're working with functions that we're going to introduce you to for the grade 11 course. But first I want to just dive a little bit further into what a function is and what it does. So certainly it's a special type of relation. Its x's aren't duplicated with different y's. But what is it in and of itself? What is it? So I want us to think about a function kind of like a machine. So our function is going to take something in. It's going to perform some set of operations on it, and then it's going to spit something different out. Okay, there's a lot of machines in real life that we use on a day-to-day basis that do that. They take something in, they change it in some way, and they give us something different out. Can anybody think of a machine in our daily lives that does that? Martez? A calculator, yeah, for sure. What about just like something at your house? Charles? Okay, so what does that do? Yeah. So we put maybe something frozen in there or something that's cold, it heats it up, and then we get out something cooked. Lauren? A printer, so what does that do?
Like you put paper in there, and then the file like kind of like goes onto it, and it comes out.
Yeah, and we have ink on it now, right? JD? Yeah, sure. How about a freezer? We can put water in there, it will freeze it, and then we get out ice, right? So this is kind of what I want us to think of a function as. It's going to be a machine. It takes something in, it will perform a set of operations. Now our operations aren't things, of course, like freezing, but our operations are multiplying, dividing, adding, subtracting, squaring, maybe. All those different kinds of operations that we do in math. So think of a function like a machine. Okay, so it's going to take in a value, and this will be like an x value. It performs a set of operations on it. And it gives us out a new value. And this is like usually our y that gets spit out from our function. Okay, so we have a special notation for this. It's called function notation, and it looks like this. And the way that we read this is we will read it f at x. Okay, or sometimes it is called f of x. I usually use f at x, but same thing. And basically what this does is it takes the place of y. Okay, so instead of something like, let's say, y equals 4x plus 1, like an equation of a line, we would instead have maybe something like f at x equals 4x plus 1. Those two things are the same thing. It's just that we're using function notation in the second one. So one really important thing to note about this is that it's not f times x, because we've been trained in, like, ever since maybe grade 8 or grade 9 that if we see brackets it means multiplication, right? But in function notation it's not f times x. F is really just the name of a function, and the x is what we're inputting into the function. So remember we said it takes in a value. Function notation tells us what value it's taking in. It's taking in x. So this is not f times x. Okay, we want to think of f as as if it's like the name of the function, and x is telling us what the input is. Okay, so you might be asking yourself, why do I need this notation? Like, why don't we just use y? There's a couple things that this is useful for. Firstly, this is actually like what mathematicians use much more than y. So you're going to see this all the time. So it's, of course, important that we know that. That way, when we're reading mathematical language, we can understand what that is. But more importantly, it's actually better than y, because when I plug something in for x, I can actually visually see. If I plug in x equals 3, I can see I'm evaluating the function f at 3. So if I have y equals 4x plus 1, the only way I know that I'm evaluating when x equals 3 is if the next line has a 3 inputted for x. But in this case, if I evaluate f at the next value of 3, I will actually see f at 3 equals such and such thing. So we can actually visibly see what the input is inside that function. And sometimes we can also use this function notation to show a relationship between two things in an actual application. So for instance, if I'm tracking height on the y-axis and time on the x-axis, I can call my function h at t, height at time. So that's really good for like applications to actually make a connection between what it is that we're tracking. Okay, so how do we use this? Let's take a look. Okay, so the question is asking us for examples 1 and 2, we're going to find f at 1 and f at 5. So if I want to find f at 1, I will basically tell what I'm evaluating, and this is basically just saying you're putting in 1 in for x in the function. So this basically just means plug in 1 for x in the function. Okay, so wherever I see an x in my function, I will sub in 1, and then I'm going to calculate. So it'll be 4 times 1 plus 3, which gives us 7. So I can say f at 1 equals 7. So the function's value, when I input 1, gives me out 7. That's what it's telling us. Josh?
Why does the x, why is it in 1?
So the question asks us to evaluate f at 1 up here. Okay, so this is actually another benefit of function notation, is that I can actually see the full x, y coordinate of the point that I'm calculating in this function just from that last line, f at 1 equals 7. This is telling me that the point on f at x is actually 1, 7. That's a point on the function right there, 1, 7. So essentially, this just replaces y. This is no different than us just like plugging in x as we usually have before, okay? So don't get confused by it. It's just a bit of a different notation that we're using now. Okay? It also asks us in the question to calculate f at 5, so we're going to do that here. F at 5, and that just means I'm plugging in 5 for the x on the right side. So this will be 23. Okay? I don't divide out 5, because remember we talked about this is not f times 5. This is the function evaluated at an x value of 5. So we don't have to isolate for x or anything like that. It's just f at 5 equals 23. And that gives me a point on the equation. It gives me a point on the line 5, 23. Okay, so don't try to divide that out or anything like that. We don't need to do that. Okay. So for example 2, we have f at x equals 11. We're asked to find f at 1 and f at 5. So f at 1, now you'll notice that there's actually no x value in the right side of the equation. So it's just equal to 11. So this is a point as well. There's a point 1, 11 on this relation. Okay, f at 5. This is also equal to 11. Okay, there is a point on this relation, 5, 11. Now, maybe if we put this in terms of something that you've seen before. What is the function y equals 11? What does that look like on a graph? Y equals 11. Josh?
It's a straight vertical line.
Close.
Or horizontal.
Horizontal, yeah. So it's actually like a constant function, right? That goes through 11 on the y-axis. So this is the function f at x equals 11, or in other words, y equals 11, same thing. It's just a horizontal line that goes through 11. So every x coordinate, no matter what that x coordinate is, will be like 1, 11, 2, 11, 3, 11, 4, 11, and so on, right? That's why we keep getting 11 for both of these. Okay, for example 3, it asks us to calculate g at 3 and g at 2. Now, I don't need to call every function f at x. I can call functions like whatever I want to call them. Like I could call them, we use like g at x sometimes, we use h at x, r at x, it doesn't matter. But the function, whatever I put inside these brackets, usually has something to do with what's over here. So notice that this one's called g at z, and then I have z's over here. So I wouldn't have g at z equals and then stuff to do with x, right? Because I'm saying that we're plugging in z's, so it only makes sense that over here I have z's in my equation. Okay, so we're going to calculate g at 3 to start. That's what the question asks, which means that we're going to plug in 3 for the z's. And then we're just going to simplify. So 3 times 3 is 9, and then we'll have 9 plus 4 on the bottom, so 13. Okay, and then g at 2, and subbing in 2 for your z's. We'll get 6 over 8, which we can reduce to 3 over 4. Okay, any questions so far? Lauren.
If it's a fraction, what would the point be then?
So we can say, like for instance, this one would be like 2 3/4, or if you do 3 divided by 4 in your calculator, it would be 0.75. So, yeah. Okay, let's take a look at another one. So this is actually a perfect example of what I was talking about earlier. So how sometimes we use like different variables to represent different things. So suppose maybe we are looking at height versus time. So h at t. This is asking us to find the domain and range. So going back to something that we talked about yesterday. Does anybody recognize this format for this equation? So we could distribute to expand. But what type of function is this, or relation? Charles? That's okay. Let's think about it in terms of something that you guys did last year. Maybe this will look more familiar. What kind of function is this? Yeah, it's a parabola. And you guys learned 3 forms of a quadratic last year. Charles? It's in vertex form, yeah. But in this...
Nowhere near that.
So this is in vertex form, and it's also in function notation for us. So what does vertex form tell us? What information do we know? Josh? Okay, so what's our vertex?
-3, x is 1, y is -5.
Do you guys agree?
I think
Is
so.
he right?
Yeah.
I think so.
A
Wait,
is negative
it's
5.
either that or -1 and 5.
It is -1 and +5,
Yes.
yeah. The one in the brackets gets flipped. What does the -3 tell us about this quadratic? It does give us some information. Page, right?
Doesn't it mean it opens down?
Yeah, actually, the -3 tells us the direction of the opening. So we know from the -3 that the quadratic opens down. Perfect. So if I go to actually graph this, because that's really the only way that I can kind of accurately see what the domain and range are, I want to graph this guy. I'm going to plot the vertex at -1, 5. Now I'm just doing like a really basic sketch here. We don't need tons of information. And I want to draw it opening down because of that -3. So I'm just going to do this. So I think from that like really general sketch, we can actually get the domain and range. Someone want to help us with domain? Martez?
So you do the squiggly line,
Yep.
you do the X, E, the weird E,
Mhm.
the R, the extra line, then you do, it would be infinite. It would just,
Yeah.
you just end it off.
Yeah, so we'll just finish it. This is going to keep getting wider and wider and wider forever toward the left and toward the right. So no left and right boundaries for domain. How about range? Someone want to help us with that one? Charles? Yep. And then close it? Is it infinite?
No, it ends up.
So do we have a bottom boundary here?
No.
Do we have an upper boundary? It starts with a C. Sorry. Carter, yes. Okay, what's the top boundary? 5. So how can I say this in mathematical language? What do we need y to be? Go ahead, Carter. Great, so y is less than or equal to 5. And then we'll close it off. Perfect. Okay, and the second part of this asks us to find h at 7. So can somebody guide me here? What would I be trying to do here? What would I be plugging in?
You
Zach, go ahead.
plug in. You plug in the T or the H? The H you plug like you replace 7 for the H.
You tell me.
That would make no sense. Never mind. You replace the T, right?
Yeah.
Okay,
That's not what.
so we're going to replace the t with 7.
I'm like, that doesn't make any sense. Just 7.
And then we're just going to simplify. So 8 squared is 64. And then what's that going to give us? 12, so 102.
-147 plus 5.
147?
147. 147.
Yeah, plus 5, right?
Yep.
Okay. So we get -142. So this actually gives us an actual point on this function, right? So there's actually a point on this parabola at 7, -142. So if we were to imagine this graph like continuing down here, and so on, at 7, once it gets wide enough, let's just say maybe this is 7, we have a point all the way down here at -142. That's what it's telling me.
It's incorrect.
Oh, is it?
It's -187, it's not 4. because-
Oh, 187, so 182. Thank you. Right? No, isn't it 97?
It's -192 and 5 is -187. So that is 192.
192.
Yeah, 192.
I was going to say, I thought, Okay, perfect. And then negative 187, right? Perfect. Thank you for pointing that out.
I got negative 187. Yeah, that's right.
Yeah,
That's right.
that's right. We got it figured out.
There we go.
Much better. Okay, can I scroll?
Yeah.
Okay. So, I know you guys haven't heard about this before, but I'm going to take some guesses. One of these functions is continuous, and one of these functions is discontinuous. Which do you think is which, and why? Sheila, what do you think?
The red one is discontinuous because there's points at the end.
Okay. So Sheila's guess is that this one over on the right is discontinuous because it doesn't have arrows on the end. Charles, what do you think? Okay. So Charles is saying that with that information, he says the one on the left is continuous because it has arrows and it continues. Any other thoughts as to which is which here? You guys agree with Charles and Sheila? Y'all are wrong. Okay, this one is the discontinuous one. This one is the continuous. Can anybody guess why that might be, now that you know? Cameron, what do you think?
I think maybe the red one's continuous because it actually continues to the end, something to end the function or whatever.
So you think the red one is continuous because, sorry, say that one more time.
It ends at like a certain point, so it's continuous. It continues to the end.
It continues to the end, maybe, kind of. Okay, here's the general rule of thumb. If a function is continuous, I can trace from the left side of that function to the right side of that function without lifting my pencil. Okay, so with this red one over here, I can trace all the way from here to here without having to lift my pencil. With this blue one, I actually have to physically lift my pen to get to the second part of this, and that's why the left one is discontinuous and the right one is continuous, okay? It's a little tricky because we're used to the idea of continuous, meaning it continues forever, right? But as long as I can get from one end of the function to the other end without having to lift my pen, I'm good. Okay, so I want you guys to see if you can make your own example of continuous and discontinuous. Okay, what'd you guys write for your continuous one? Just like this? Something like that? Yep. So something maybe like this. Okay, that one's continuous. Perfect. Anyone have an example of discontinuous for us? Charles?
I just feel like I have to miss.
Sure. So is this a function actually? This asks us for a discontinuous function.
Yeah.
Uh-oh. That doesn't pass the vertical line test, does it? Sad face. Discontinuous function. Who has a discontinuous function? Charles gave us a discontinuous relation.
Can you just do vertical lines?
That's also not a function, right? Because any vertical line will intersect continuously.
Yes.
Oh,
How about just like a set of
that was a bad
points?
idea.
Is this discontinuous?
Yeah, I can see.
Yeah.
Wait, just dots?
Yeah, just points, right? Or even if it had like two pieces, like it went like this, and then it went like this, that would be discontinuous. Okay, go for it. Okay, so Zach said this as well. So Zach said, how about just vertical lines like this? Is this a function? It is? Do you say yes?
Yes.
But if I draw a vertical line over top of a vertical line, those things infinitely intersect. That doesn't pass the vertical line test, right? So vertical lines are actually not functions. They are undefined, like lines with undefined slopes, technically. Let me know if you think of another one, though. Okay, let's move forward. Okay, function or not a function? Is this a relation or can it be further classified as a function? What do you guys think? This is a function, yeah. Okay, so for this function, this is going to be the function or the graph of the function f at x. This is asking us to find f at 0, f at 3, and f at 6. So when I'm asked to find f at 0, here is the question in plain English. What is y when x is 0? So you guys say 0? Yeah, and that's because we have a point at 0, 0, right? So f at 0 equals 0. Perfect. F at 3. I heard it back there somewhere. 4. Thank you, Matt. F at 3 equals 4, and you guys can see here on the function, on the graph, when x is 3, y is 4. Okay, how about f at 6?
2.
That's right. Okay, so when we see f at 6 here, when x equals 6, y equals 2. So f at 6 is 2. Perfect. So again, these are just points on a graph, right? That's what we're talking about when we're thinking about function notation. Are we all good with that? Any questions? Can I scroll? No? Okay. Okay. Function or not a function? Okay, so this one is, I'm doing a bunch of little tricky things with you guys today. So this one, it actually might be kind of hard to see on your papers there, but this one has a couple hollow points. And what these mean is that the point that is defined at, let's say, 1 or 9 is actually the solid point. The hollow point means we actually just continue through it and go up to where we find a solid point for that. So it's defined all the way up to 1.000001, but once we hit 1, we jump up to 5. So because I have hollow points here and here, those actually do pass the vertical line test, because this little hollow point down here is undefined. This is the point that's defined. Okay? So if you see a little hollow point, you're going to see them along your travels. It basically just means that little point is undefined, and then you find where it's a solid point along your function. So this one actually does technically pass the vertical line test, because these two guys here are undefined hollow points. So this is a function, actually.
If those points were not hollow,
Then it would be just a relation and not a function. Is this continuous or discontinuous? How about the previous one? Was that continuous or discontinuous?
Discontinuous.
The previous one?
No, the previous one was continuous.
The previous one was continuous, yeah. Okay, so can somebody tell me what f at 3 is equal to for this function? Matt? Yeah, so the point 3 has a y-coordinate of 2. Perfect. For f at 1, when x is 1, like I said, when we have this little like hollow point here, we will go up through that point until we hit an actual solid defined point. So f at 1 will be 5, yeah. Okay, so that's the point right here that would be actually defined for f at 1. How about f at 6? F at 6 is 6 because when x is 6, y is also 6. And f at 9? F at 9 is indeed 9 right here. Perfect. Any questions for that one? Okay? Yeah, Matt, sorry.
So does whether it's negative or not on the graph not really matter?
Sorry, say that one more time.
Because like you said, f3 equals 2.
Mhm.
F3 on the graph is negative 3.
So even though this is like a line over here, like this, shh, guys, listen. So the question was, f at negative 3 has an actual point on it, but f at 3 was just like a line here. It doesn't mean that there's no point there if it's just a line. There is still a point technically on that line. Yeah, good question. So we're looking at where f at 3 is there. Other questions, anything? Okay, so in your workbook, I'm just gonna flip over to that here. I'm not gonna have you do everything here, so if you guys wanna grab your workbook, I'm gonna circle a couple questions, you can circle them. Shut the video off here.